Okay, so we're going to start derivatives today. That is the second of the three major topics in calculus. We just finished limits. We're good to go with that. I'm of the opinion that limits was fairly conceptual, less mechanical. Derivatives is the exact opposite. It's more mechanical, less conceptual. However, today we do need to do some conceptual stuff to understand why we're doing this. From today forward, it's going to be a lot of mechanical stuff. By mechanical stuff, I mean grinding out derivatives, doing the derivative over and over again. Okay, so for that worksheet, you started with a parabola. Hopefully you realize that that parabola opens upside down. Negative x squared, help me out, plus 4x plus 3? Yes. Plus 4x plus 3. First question I asked you is, where's the vertex? Your answer is? 2, 7. Where'd that come from, Matt?
One second, my brain's still working.
Do I need to call somebody?
No, I'm good.
Okay.
So you...
Strike two. Hey, bada, 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 swing, bada.
Wait.
Okay, now it's gotten awkward for everybody.
Yeah, I'm going to stop now.
Why is it 2, 7? Anybody else? Thank you. Negative b over 2a. I just lost the ability to write the number 2. Okay, negative b over 2a gives you the x value of the vertex of that parabola, and therefore you plug the 2 back in and you get 2 comma 7. Okay. How do I know the vertex, how do I know the parabola opens downward?
The negative and the x squared.
Beautiful. The negative a term tells me it opens up downward. Okay, good. So what that activity was asking you to do is to calculate a bunch of slopes. And so we've talked already about the difference between tangent lines and secant lines. So if I draw in something like this blue line, that is a tangent line to the right of the vertex. What would, wait, let me rephrase that. What can you tell me about the tangent line at 2, 7?
Slope is 0.
Why? Who's talking?
Because it's like it's on a curve, and it only can touch one point, so it's horizontal.
Ah, there's the key. I totally missed. Okay. Does everybody see why that line has a slope of 0? It's the top of the parabola, therefore it's a horizontal line, and we know a horizontal line has a slope of 0. And then if I move to the left of that vertex, and I draw in another tangent line, I would get something like, let's say, this. What can you tell me about the slope of that blue line?
It's a negative slope.
Negative slope. What can you tell me about the slope of the green line? Positive slope. Okay. If I was able to take that blue line and roll it along the parabola, hopefully you all see that that slope would change, yes? It goes from a very big positive number way over here. It starts to get smaller and smaller, hits 0 at 2, 7, and then continues down, down, down into a very big negative number. Okay? What I mean by that is that depending on the point on the curve you're talking about, the tangent line has a different slope. Over here, the tangent line would be a fairly big positive number. We talked about 0 already. Over here, negative slope. Over here at the green, we would have a positive slope. Okay? Now, one of the things that causes problems for people as we start talking about the derivative is the idea we're not always going to get a slope that's numerical. Okay? We're going to get slopes that are equations, and that bothers people. And you might be confused, but bear with me, I'll get there eventually. Okay? Questions so far? All right, good. So, you had this equation then, and you were asked to solve the equation. That guy up there, get me some working room here. So the limit, nope, go back there, thank you. the limit as delta x approaches 0 of f of x. Which one did I give you? F of x plus delta x? Yeah, okay. We've seen a plus h. We've seen x plus a. This one I happen to choose the format of x plus delta x because that's the format I like. So negative x plus delta x quantity squared plus 4 times x plus delta x plus 3 minus parentheses negative x squared plus 4x plus 3 all over delta x. Sorry, I was a little crammed in that corner there. And remember, f of x plus delta x is you go to the function, wherever you see an x, you put in an x plus delta x. These parentheses are very important. Okay, now the fun begins. Limit as delta x approaches 0 of negative x squared minus 2x delta x minus delta x squared. I'm tired. I hope I did it right. Okay, what did I just do? Math. Good. I squared the binomial and I distributed the minus sign at the same time. Pretty good that way. Then I distributed the 4. Then I distributed the minus sign. And then I got a train wreck. But once I change colors, wha-bam, 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 wha-bam. Boom, things start dropping out. That makes me happy. Now, you'll notice I didn't plug and chug first. I should have, I'm sorry. But I know what would happen. If I plugged and chugged right away, I'd get 0 over 0. That's no good. If I plugged and chugged here, I'd still get 0 over 0 because I have to do some more math. The limit as delta x approaches 0 of delta x times, Gesundheit, change colors again, whoop-bam, whoop-bam, equals, what's the limit of that stuff in the parentheses when delta x goes to 0?
Negative 2x plus 4.
Who's talking? Thank you. Negative 2x plus 4. We just did our first derivative. Yay! High five. Good job. I'm very excited. I love derivatives. That was fun, wasn't it?
Define fun.
Define fun.
Yeah.
That's a discussion for another period. Okay. So, next screen. Why did we do a derivative? Well, one of the things we're going to learn is a derivative serves 3 purposes. Derivative. Why did my R just disappear? Who cares? Number 1. Oh, my V's back now. What the hell? Slope of the tangent line to the graph of a function. Things are disappearing and I'm not happy. You're seeing this happen, right?
Yes.
Okay, it disappears and then it comes back. So if I just wait long enough, it'll be good. Okay, 2 and tree. We'll come back to 2 and tree in a couple minutes, but that's the first one. It's the slope of the tangent line to the graph of a function. Okay. Now, this is what I was talking about before. This is a slope. Well, that's weird. That's not a slope. It is a slope. Because, like we talked about, if you look at that parabola, the slope will change at different locations. So, just for giggles, we know one of the answers. The purple line, the slope at 2, 7 should be 0. Negative 2 times 2 is negative 4 plus 4 is 0. Yay! That makes me happy. Okay, so that's the first thing. Second thing, who's in physics right now? Loving it, right?
It's great.
Good. Awesome. So, let's talk some physics. I don't know how those weirdos in physics do things, but I'm just going to talk about math. In math, we use the equation S of t as a position function. You know that term, yes? Position function? Does anybody not? Is anybody not in physics? Or hasn't taken it? Okay, so I'll use smaller words. This is the position function, which means where is an object at any certain point in time. Okay? So if I pick up Mav and throw him out the window, there's a function that would define the path that he follows on his way down to the roof below us. We could calculate how long it would take him to hit the roof below us. We could calculate how fast he was going when he hit the roof. We could calculate all kinds of different things because there is an equation for that. Okay.
Was that a threat?
What's that?
Was that a threat?
No, that was an if,
Oh, okay.
not when. When would be a threat.
Okay, yeah.
If is just a hypothetical
Okay,
scenario.
Gotcha.
Okay. So, if I take the derivative of the position... Oh, wait. Okay, hold on. Sidebar. Do you know what a sidebar is? It's when you come over here on the side and you talk a little bit. Some notation. If we have a function f of x, its derivative is written as f prime of x. Okay. Easy peasy. It would be nice if we just had that. But because of a weird scenario, there's actually different ways to write that. Let's suppose we have a function y. The derivative of y would be dy dx. You're asking your kids.
2 seconds to get your
1, 2, time's up.
I have a field trip for the 30.
Oh, excellent. Here, hold that. D minus?
Probably.
Okay.
I can pull the rest of that out.
You're telling me my job. You don't fight.
Not especially.
Don't wait until they're busy.
Thank you very much. Have a nice day.
Okay. So you're saying to yourself, Self, why are there two different notations? That's a great question. The answer to that question will be covered later when we have a brief history lesson. Okay? Not now. All I need you to know is that there are two different ways to represent this. What if it's not f of x? What if it's s of t? It's just s prime. You just stick a prime on it. Okay? So the derivative of the position function gives us the velocity function. So if I had the equation of Mav flying out the window, I could take the derivative of that and calculate how fast he's going. Anybody know what happens when you take the derivative of the velocity?
Acceleration.
Acceleration. Okay. Meters per second per second. Oh, wait. So I'm taking the derivative of a derivative. What would the notation be there?
Double prime.
Double prime. S double prime of t. Just to see if you've learned anything in physics. This is calculus, but physics. Does anybody know what the derivative of acceleration is?
G.
I'm sorry, what?
Sure.
What'd you call me? Huh? You're, it's called jerk. We don't care. That's for them. We stopped acceleration. Okay? So, in this slide, we got all that wrapped up, that it's a derivative of the position function. So we go back to this screen, and we say, step 2, it is the instantaneous velocity. That's the wrong yellow. Okay, but that's okay. For some reason, I lost my 3. It's back. We'll save 3 for later. Okay. Any problems? If we have the equation for throwing Mav out the window, if I take the derivative, I'll know exactly how fast he's going at any point in time. That speed changes once he launches out the window. You understand that from physics, right? If I throw him out the window, let's not be so violent. If I drop him out the window, his initial velocity is 0. He accelerates, which means his velocity changes. When is he traveling the fastest?
Right before it hits.
right before he hits the ground, assuming he doesn't reach terminal velocity, and that's a whole nother discussion which I don't want to talk about. But so the same concept is true with the parabola. The derivative changes at all different points in time. Mav's velocity changes at different points in time. His initial velocity at 0 is 0. By the time he hits the roof, he's going to have a different velocity. Halfway down, he's going to have a different velocity, et cetera, et cetera, et cetera. Okay, that comes from the derivative. You good with that so far? All right, good. So let's take a look at one more example, and then we'll be done. I can do this in 9 minutes. Let's simplify things a little bit more and say we'll take a function x squared, and I'd like to know the equation of the tangent line 2x squared at 3, 9. First of all, I assume you all agree with me that 3, 9 is on the curve, right? Because 3 squared is 9. Beautiful. All right, here we go. What are the two things you need for the equation of a line? Slope and y-intercept, but we could actually use any point, right? So a slope and a point. You're going to hear me say that a gabillion times. Slope and point. I have the point. Yay! How do I get the slope? I take the derivative. How do I take the derivative? This monstrosity. The limit as delta x approaches 0 of x plus delta x squared minus parentheses x squared. And I know you're saying to yourself, why did he put those last parentheses in there? Because it's a good habit to get in. As the functions get uglier, you're going to need those parentheses. I would argue that I probably should have done this one earlier because that was just bleh. But that's okay. This will be fine. It'll be a nice, pleasant way to end the class. Whoopsh, whoopsh. What's the limit? 2x. All done. No, I'm not all done. Sorry. I'm done with the derivative. Okay. But again, I got an equation. How do I find the slope? Anyone? Bueller? I'm not giving you this one.
Change in X over change in Y.
Oh, I don't know what change in y is.
Oh.
Yeah. How do I find the slope at 3, 9? Now it's getting really awkward. So be-
Do you plug in 3 for the X?
Beautiful. Okay. This, as I mentioned earlier, which must not have sunk in, is the equation of the slope anywhere on that parabola. But now we're talking about a very specific point. That specific point is at 3, 9. So therefore, the slope is equal to 2 times 3, which is 6. Therefore, I get y minus 9 equals 6 times the quantity x minus 3. That is my final answer for the equation of the tangent line. Point and slope. The slope comes from the derivative. The point is given information. This limit thing is a pain in the butt, especially when it gets ugly like that guy. So, one of the things that we're going to do in the rest of this chapter is learn tricks to make your life a lot easier. Some of you might already know the tricks from this is calculus, the other one, physics. but we'll get there eventually. We'll also learn eventually what the third thing that a derivative does. Okay, but that comes later. Questions? Beautiful. With this chapter, what I've done is, this is probably the most important topic in calculus. That's why we're going to spend like 2 months on it. So I've changed some things from what we did in the last chapter, and that is I've stretched things out a little bit more. Because a lot of these problems are mechanical in nature, you have to get in there and grind out this homework. Okay, some of you have been giving me homework that kind of looks like the answer key that I gave you. All right, you're not learning anything from that. The only way you're going to learn is by practicing this homework. So as you get into the homework, you have to actually do the homework. It's going to be messy. You're going to make mistakes. Mistakes are encouraged. That's why you have an eraser. Okay, or you have you're digital, so you don't have an eraser. You know what I meant by that. Okay, questions? I'll try to get your test graded for you. I should have them back by, today's Thursday. I have no problems getting them to you by Monday. I'll probably have them done early. If I have them done early, I'll throw the scores up on the interwebs for you to examine.